Biggest perfect square factor that goes into 72. Nope. 36 is the biggest one that goes into 72. It goes in there twice. So the answer here then would be 6 times the square root of 2. If you went the 9 route, if you went 9 is multiplied by 8, okay? If you gave me 3 times the square root of 8, you would be wrong, because 8 has in it 4 as a perfect square. Then I get 6 times the square root of 2 if I go even further. I mean, you can do the 9 and 8 method, but don't just stop after you do it once. Oh, I'm done. Okay? You have to go until you can't go anymore. Okay? 3 times the square root of 8 simplifies to be 3 times the square root of 4 times the square root of 2, which the square root of 4 is 2, so this becomes 6 times the square root of 2. 2 times the square root of 20 is 2 times the square root of 4 times the square root of 5, which is 4 times the square root of 5. 5 times the square root of 50 is 5 times the square root of 25 times the square root of 2, which is that's 25 actually, times the square root of 2, because it's 5 times 5. Can I combine any of those two? What do I have to look at? If I'm adding and subtracting, what do I have to look at? The radicans, right? Do I have any like radicans? Yeah, I got 2 of them, okay? I got 2 2's. So this could be negative 19 times the square root of 2 plus 4 times the square root of 5. Or I would also accept 4 times the square root of 5 minus 19 times the square root of 2, depending on which order you want to write it in. Oops, I went down a little too far. The square root of 10 times the square root of 40. Well, the square root of 40 is the square root of 4 times the square root of 10. So then this could be written as the square root of 10 over 2 times the square root of 10. And then those square roots of 10 would cancel each other out, giving me 1/2 as my answer. Another way of doing it, we could use that property that we had on Monday, and we could write this as a big square root of 10/40ths, which then simplifies to be a big square root of 1/4, which then becomes the square root of 1 over the square root of 4, and the square root of 1 is 1, the square root of 4 is 2, so that leaves me with 1/2. Okay.
You just get rid of the zeros and go from there?
In this particular case, yes, because you're basically doing this green method there, and then you're chopping off the zeros. Yep. As long as they're trailing and they're both inside a radical. Yes. Okay. Love it.
Linz, I have a question.
I got an answer.
Okay, for that one, I did it a completely different way.
Which way?
I just multiplied the numerator and denominator by the square root of 40.
Okay. So at the top you got the square root of 400
Yeah.
over the square root, or basically over 40 then, right?
Yeah.
Okay, that works too. Yep. And then simplified the square root of 400 as 20.
Yeah.
And then 20 over 40 reduces down to 1/2. Yep, that works too. Yep, more than one way to get to Mosinee from here. Yep. So today, what we're going to be doing is we're going to be kicking it up a notch, and we're going to be going into some more in-depth radicals. Okay? And so, like third roots and fourth roots and possibly some fifth or sixth roots or seventh roots, or I think there's a one homework problem that's a seventh root. Okay? All right? So, when we're doing those, I'm going to move this one over just a little bit. Okay? When we're doing multiple roots, like the other day, we said if we have square roots, we said we looked for perfect square factors, right? And our perfect square factors were 1 and 4 and 9 and 16 and 25 and 36 and 49 and so on and so forth, right? And we have a list of those from Monday. Okay? All right? Well, now, when I have a third root, I'm going to look for a perfect third. 1 is a perfect third. Doesn't really help me, but it is. 8 is a perfect third, or a perfect cube. 27, 64, 125, 216, 343. That gets me to 7. 8 is 512. Nine is 729. 10 is 1,000. Those are the perfect thirds. Fourths. I go with the one blue. One. 16. 81. 256, 625, I think it's 1,096. 216 times 6 is, yep, nope, 1,296. 343 times 7 is 2,401. Probably won't ever have to use these big ones. $4,096. $6,561. 10,000. So those are the factors then that you're looking for in those. Okay? So if I were looking here at the cube root of 48, now I'm going to look down that red column and I'm going to look for the biggest number that evenly divides into 48. Well, 8 does. So this becomes the cube root of 8 times the cube root of 6, because 8 times 6 is 48. Just to make sure, I look down that red column again to make sure that there's none that go into 6. And the only one that goes into 6 is 1. So that gets me done there. So the cube root of 8 is 2. 2 times 2 times 2 is 8. So the cube root of 8 is 2. So the cube root of 48 is 2 times the cube root of 6. You try the fourth root of 80. So I got the biggest perfect fourth, so I'm looking in the blue column now. The biggest perfect fourth that goes into 80 is 16. It goes in there 5 times, so this becomes 2. So this is 2 times the fourth root of 5. Now, my question to you is this. What if, and I know that this happened to some people because I have 2 eyes that work and can see out farther than 5 feet. What if you didn't write down the list? The list of perfect cubes, the list of perfect squares, the list of perfect fourths. Okay? What if you didn't write that down? How could you go about finding me the third root of 48 and the fourth root of 80? How can I go about doing those exact same 2 problems without having a list to go off of? How can I do that? So if I do a tree, which one do you want to do first? Left or right? 48. Okay. So if I do the tree thing, right? So then 48 would be, what, 2 times 24? And 24 is 2 times 12. And 12 is 2 times 6. Oops, I got to go down a little bit more. Guess I can't. Guess I got to extend a little bit. And 6 is 2 times 3. So now how many do I, like, on Monday we were looking for pairs. Now I got to have 3 of them because my index is 3. So there's my 3 that make my 2. And then these 2 are still left over. So then out of that would come 2 times the cube root of 6. Okay? 80, we can do 80 the exact same way. 80 is 2 times 40. 40 is 2 times 20. 20 is 2 times 10. 10 is 2 times 5. But now I'm looking for groups of 4 because my index is 4. So here's my group of 4. And then what's left over? So then this would become 2 times the fourth root of 5. So it can be done without the list. You just have to know what your prime factorizations are of your numbers. Okay? Try those 2. Cube root of 24 is the cube root of 8 times the cube root of 3. The cube root of 8 is 2. So this would become 2 times the cube root of 3. The cube root of 16 is the cube root of 8 times the cube root of 2. Again, the cube root of 8 is 2. So then this would be times 2 times the cube root of 2. Outside, I get 4, 2 times 2. And inside, I get the cube root of 6. Outsides go with outsides, insides go with insides. That stays the same as the other day.
Could you do 24 times 16?
You could do 24 times 16 first and get a big number, and then go from there with it, yes. Okay? Yep, that's another way of getting to the exact same location. Yep. Okay. Fourth root of 2, there is no perfect 4 factors that go into 2, so that stays the same. Same with the fourth root of 40. There are no perfect square or perfect 4 factors or perfect fourth factors that go into the square root of, or the fourth root of 40, excuse me. So this becomes 21 times the fourth root of 80. But when I do that, I've got to check that there are no perfect 4 factors now that go into 80. Well, there is. This becomes 21 times the fourth root of 16 times the fourth root of 5. And this becomes 2. So I get 21 times 2 times the fourth root of 5, which is 42 times the fourth root of 5. Yes, sir. Yes. The index here, if you forgot the 4, yep, because now you're talking something totally different. The fourth root of 5 is not equal to the square root of 5. Yep. So yes, that index is extremely important. Same thing if it were an exponent. You know, if x squared is not the same as x to the fourth. So, yep, it means it has that same gravitas. Okay? Don't like radicals in the denominator. Okay? Just like before. Don't like radicals in the denominator. Before we said when we were taking the square roots, we just multiplied by the square root of whatever it was to clear it. Well, the downfall here is that if I were to multiply both here, top and bottom, by the cube root of 6, I get on top 2 times the cube root of 6. Do we all agree with that on top? On the bottom, I get the cube root of 36. And does that show up in my cubic column here? Or that one that we wrote down? It doesn't show up. So that doesn't do me any good. So instead of here multiplying by the cube root of 6 over the cube root of 6, I've got to get to the next perfect cube. So for this one, I've got to get 6 all the way, somehow by multiplication, to, oops, not to 36, excuse me, pardon moi. I got to get it to the next one that it goes into. Well, it doesn't go into 1, doesn't go into 8, doesn't go into 27. I got to get it all the way to 216, because that's the next biggest perfect cube that it goes into, right? So 6 times what gets me to 216? 36. So here, I'm going to multiply by the cube root of 36 over the cube root of 36. Because now on top, I get, let me bring this down a little bit, 2 times the cube root of 36 over the cube root of 216. 216 is on my list. It's the cube of 6. So this becomes 2 times the cube root of 36 over 6. Is that an acceptable answer? Why not? What cancels? The 2 and the 6, because they're both outside, right? So 2 goes into 2 one time. 2 goes into 6 3 times. So the acceptable answer here is the cube root of 36 over 3. Okay. What I'd like you to do now is I'd like you to try number 6. I'm guessing, just guessing here, that most of you chose to multiply by the cube root of 16 over the cube root of 16. Anybody choose that method? Okay, all right. And that's fine. Okay, I can do the cube root of 16 over the cube root of 16 because that then gives me 7 times the cube root of 16 over the cube root of 64, and that's good because the cube root of 64 is, cube root of 64 is 4, but 16 has the cube root of 8 in it, and the cube root of 8 is 2. So this really becomes 14 times the cube root of 2 all over 4, which reduces down to 7 cube roots of 2 over 2. Now, a few of you were kind of shaking me off there when I said the cube root of 16 over the cube root of 16. Let me rewrite it here. 7 cube root of 4. Brett, what did you multiply by?
Square or cube root of 2.
Over a cube root of 2? Yeah, because the cube root of 2 over the cube root of 2 still multiplying by 1. So it's still legal there. Top here becomes 7 cube root of 2. Bottom becomes the cube root of 8, which is 2. And I get right there. Okay? Both methods work. Okay? Both methods work. One just takes the simplifications out at the end. Okay? And that really is just knowing, all right, so I was at 4. I can multiply 4 by 16 and get to 64, or I can multiply 4 by 2 and get to 8, and both of those are on my list. Okay? I just need to get that denominator to a perfect indexed number. Okay? So there are 2 forms of radicals. First thing I want to do is I want to add in here a box, and I want my box to be green. There we go. Perfect. Okay. So we've been dealing with radical form, and that's great. Okay? But we can write the same term in exponent form. So I take my radicand, and it becomes my base. So the inside of my radicand, or the base inside the radicand is there. If I have an exponent, it becomes the numerator, and my index becomes the denominator in my new exponent. So if this were, and I'm going kind of quick through this because this should not have been the first time that you've seen this. If this were the 7th root of x to the 5th power, in radical form it looks like the 7th root of x to the 5th power. In exponent form, it looks like x to the 5/7 power. And vice versa. Okay. So if I ask you to rewrite the square root of 37 in exponent form, the base is going to be 37. My exponent on 37 is 1. So that's going to be to the 1. And my index is 2, even though it's not written. So it's going to be 37 to the 1/2 power. Number 8. What would number 8 be? Is that going to be your final answer of 27 to the 1/4 power? Why not? So is 1/2. Reduce what? What would it reduce to? But that's different. That's 27 times 1/4. I want 27 to the 1/4 power. 27 show up anywhere else? 27 show up anywhere else? It's a perfect cube, right? It's a cube of what? 3. So this is really 3 cubed to the 1/4 power. Exponent rules come into play again, right? What do I do with a power to a power? What? Multiply them. So this becomes 3 to the 3/4 power. Now, why do we do this? Well, we do this, I give you one, right? Okay. We do this because if I have the 4th root of x times the 4th root, or excuse me, times the 3rd root of x, I can't do anything with those because they have different indexes, right? But if I put them into exponent form, now I can do something with them. And I can add the exponents and get it into one radical. Okay? That's why we do this. Okay? Variables is the other thing. Okay? And for variables, my question to you is, a variable, or really it's not a question, it's a statement. A variable is perfect if the exponent is what? So I really didn't make it into a question. So a variable is perfect if the exponent is what? They're all going to be positive because we don't like negative exponents. Don't know? Let's try one. See if we can come up with it as we go along. So square root of 8 times the square root of 3. Well, that becomes the square root of 8 times the square root of x cubed. I think I said that wrong, but the square root of 8x cubed becomes the square root of 8 times the square root of x cubed, right? Agree with that statement? Okay, well, what? Nope, not the same. We're getting there, though. Okay? So square root of 8, that's what? The square root of 4 times the square root of 2? Square root of 4 is 2. Okay. Square root of x cubed. Isn't that the square root of x cubed times the square root of x? Can I write it like that? Okay. So this becomes, oops, I almost put 2 there. This becomes x. So this is 2 times the square root of 2 times x times the square root of x, which then finally gets me 2x times the square root of 2x. Yeah? Okay. Figure out what makes a variable perfect yet? What?
X squared.
In this case, it's x squared, but is it going to be x squared in the next one? No, so we can't just say x squared. All right, well, let's try this one then.
Even degree?
Hmm?
Is it an even degree?
Let's try it. An even degree, like an even exponent, you mean?
Yeah.
Okay, well, let's try it in this one, see if your even exponent works out. Okay, so this is going to be the cube root of 16 times the cube root of x to the 5th times the cube root of y squared times the cube root of z, oops, that's a z, to the 4th. Right? So, cube root of 16 is going to be the cube root of 8 times the cube root of 2. So this becomes 2. Agree with that? And I would say this next one would be the cube root of x cubed times the cube root of x squared, because then this becomes x. Whoops, didn't mean to throw it at you, Colin. So your even exponent, does that work out? No, because we've got x cubed and cubed is odd. Okay. I would say that this one stays the cube root of y squared. I would say this one becomes the cube root of z cubed and the cube root of z. This then becomes z. So here I would get 2xz times the cube root of 2x squared y squared z. Come up with it yet? What do you got?
The exponent matches the index.
Does it have to match exactly though? Let me try one, and we'll see if you're, because we're on the right page, Luke, okay? So let me see if I can come up with a good one here. So let's go with the 4th root of, we'll go 16 again, x to the 8th, y to the 7th, z to the 9th. Okay? And I would say that this would be the fourth root of 16, the fourth root of x to the 8th, the fourth root of y to the 7th, and the fourth root of z to the 9th. Agree with breaking it up like that? This one becomes 2, because it's on my list. This one becomes x squared. This one I would break up into the fourth root of y to the 4th and the fourth root of y cubed, because then this becomes y. This one I would break up into the fourth root of z to the 8th and the fourth root of z, because then this becomes z squared. Figure it out yet? Not greater. So what do we call numbers that are divisible by it? Not factors. Factors are smaller. It's an M word. Multiples. Okay? So a exponent or a variable is perfect if the exponent is a multiple of the index. So down here, just to finish off this problem, we'd have 2x squared y z squared times the fourth root of, taking care of y cubed z. And we're looking for multiples. If you think about it this way, if you think about it in terms of exponent form, if I look here at, so I went too far. If I look here at this x part, oops, we'll go purple. If I look here at this one, x to the 8th power and the fourth root thereof, that's going to be x to the 8 over 4 power if I switch it into exponent form from radical form. 8 divided by 4 is 2. Okay? So they have to be multiples in order for them to get released. Okay? Your homework today is a worksheet, okay? And I'll pass that out right now.